Yeah, recording has started.
Yes. Let's start. Thijs, the
Okay,
screen is yours.
thank you. Yeah, thank you for the introduction. As Derek in the room already said, a lot of people had been asking him yesterday during the Combustion conference, well, what is plasma-assisted combustion all about? My goal is to give a quick overview of the fundamentals behind plasma and plasma-assisted combustion. I will cut some corners here and there because it's a very diverse topic. There are many things to discuss, but I hope that after this session, you at least know what the basics is of plasma-assisted combustion, and that you can go to the next webinar from Benedict with some insight. So, what is plasma-assisted combustion and why are we interested in it? It's a method for efficient combustion activation, and why that is, I will explain during this lecture. The challenges is that there are a lot of timescales involved. We have timescales which are significantly shorter than we already are used to in combustion, and we also have spatial scales which are significantly shorter. And this makes it both for numerical models a very big challenge, and also for experiments a very big challenge. And the chemistry of plasmas is generally rather poorly understood. Myself, I do numerical research within plasma-assisted combustion. So most of this will be viewed from a point of modeling and well, numerical simulations, but I will try to give the fundamentals of it. So first off, what's a plasma? Generally, we consider that a plasma is the fourth state of matter. And I think all of you know it from this kind of beautiful globe where you have this plasma discharge. And if you put your hand on it, then the plasma tends to go to your fingers. And in that bowl is just an ionized gas. It can be both hot or cold. The sun, for example, is a hot plasma, and this globe clearly is a cold plasma. It remains roughly at room temperature, which is why you do not burn your hands. Specifically, in the case of plasma-assisted combustion, we create this plasma via an electric discharge. There are also other methods to create it, but we will only consider this. And we generally do not want to go to temperatures of the sun, so we have a relatively cold plasma. Okay, so let's say we have an electron somewhere in air, and now we apply an electric field on it. And we do this by having an electrode on the bottom and an electrode on the top, where we apply a potential difference with the bottom being the ground, and in this case, the top being a user supplied voltage. This creates an electric field, which means that then the electron is accelerated in the upward direction. At some instance, this electron reaches a velocity v, and then it can collide, for example, with oxygen. And when this happens, several things can happen. This electron has a certain amount of kinetic energy, and when it collides with the molecule, it can result in a momentum transfer. This means that the electron bumps into this molecule, and then energy is transferred to this molecule, and it moves. When you derive both the balance of energy and the balance of impulse for particle-particle collision, and you write it all out, then you see that at most you can transfer the energy of the mass of the electron divided by the mass of the molecule. Given that an electron is roughly 5 times less heavy than a molecule, you see that this energy transfer is very inefficient. However, molecules are not rigid. They are effectively two spheres connected by a spring, and they can vibrate around. So what can also happen is that this electron bumps into this molecule, and then these two atoms start vibrating around. Another option is that this electron bumps into an atom or a molecule, and then it moves an electron in the electron shells, which is a little bit of a simplification, and it creates an electronically excited state. If we go back to the case of our molecule, it can also bump really hard into it, and then it can break the bond and dissociate it. Finally, and this is what a plasma makes a plasma, it can bump into a molecule or atom and then rip off an electron. And then suddenly you have two electrons, which are then in the electric field, and the second electron also gets accelerated. If we look at this from a point of view of the kinetic energy of this molecule, of the electron, then we see that at very low energies of the electron, the chances that we have a momentum transfer, so the case where we bump into this molecule and it gets moved, is very high. If we then go to slightly higher energies, we predominantly start vibrating molecules around. If we then go to even higher energies, we might start electronic excitation, right? So we move the electron into a higher electron orbit. If you have even higher energies, the chances are becoming bigger that we start dissociating molecules. And at even higher energies, we start ionizing molecules. Okay, and then the next question is, what is the energy that this collision is going to happen at? Right, so we have an electron that just bumped off from a molecule, and we will just assume that the velocity is 0. We now have an electric field. This electron gets accelerated. And then what determines the electron energy when it hits our oxygen molecule is basically the flight time in between, because we have a constant acceleration by the electric field. And what in plasma physics is then generally defined is a reduced electric field. It's the energy, or the electric field, divided by the number density of molecules. And what you will see is that a lot of plasma behavior falls down when you compare it in terms of reduced electric field. Okay, and then it's important to consider that, okay, we have now viewed a single electron, but what if we do a lot of electrons? Then what you can solve is the Boltzmann equation, which is the distribution function of electrons, or the probability of finding an electron with a given velocity vector and momentum vector and position. So here I've shown a box on the right where we have particles with different velocities into different directions, and this F is the distribution of these. And then the Boltzmann equation is a accumulation term, which says, okay, locally we're changing the distribution function by this much. You can also imagine that if we move electrons in bulk into one direction, that we are redistributing it in space. And this is the important part in our electron cases. We can also apply acceleration to it, which are by the electric field. And finally, we have collisions or reactions. Let's say that we consider the case of only electric collisions. Then if we say that the effect of all our elastic collisions must be equal to 0, which means if you went back to the previous slide, that basically the time-dependent part and the spatial part is 0, then what you get is the Maxwell-Boltzmann distribution, which is a well-known distribution of the kinetic energy of particles in a gas at different temperatures. And what you see is that the energy is typically, well, given in electron volts, relatively low, even at 1000 Kelvin. And that when you increase the gas temperature, you start creating more high energy particles. And these high energy particles are exactly the particles which, in the case of classical combustion, dissociate molecules and provide the activation of the chemistry. If you remember from 2 slides back, there you saw that the cross-section of dissociation started at around 5 electron volts. So here I've shown these cross-sections, and you see that the dissociation, the red line here, starts at around 5 electron volts, and that's for oxygen. So if you now imagine back that distribution function, then you see that basically no or a very, very small portion of the particles has enough energy to dissociate this molecule. which means that at 1000 Kelvin, it's difficult to dissociate anything, which means that it is difficult to initiate combustion, which then leads later on to long ignition delays or slow flame speeds. If we now also consider an electron where we have a reduced electric field of 0.1 Townsend, that's a really low reduced electric field in the water plasma, then you see that we already have a population distribution function, which has higher energy particles on average. If we now go to the case where we also have 100 Townsend, which is in the case of air a little bit below breakdown, we see that we suddenly have electrons which are 5 electron volt and higher. That means that these electrons, they can have a very high energy, even when the gas temperature is relatively low, which will allow them later on to do chemical work. And if we go to even higher energies, then we start populating the tail even more. And you can get very high energy electrons that can also ionize the gas. So if you have a methane air mixture and we look at reaction rates, what we then have to do is we have to integrate this distribution function by the cross section. And then that gives and if you also introduce the collision frequency, then you have the reaction rate. And here I've shown then several reaction rates which are common in plasma. So you have the nitrogen, which forms a nitrogen vibrationally excited state, nitrogen, which forms a nitrogen electronically excited state, oxygen, which can be bumped by an electron and then starts to dissociate the oxygen molecule into oxygen atoms. And if you look at this, then you will see that it is around 1 times 1e15 cubic centimeter per mole per second. If you then look at this reaction rate normally in oxygen, in an oxygen nitrogen environment, then at 2000 Kelvin, this reaction rate is only 1e minus 4, which means that these electrons, they can not only do chemical work at a low temperature, but they can also do it at a, well, almost ridiculously high rate, even though the electron concentration is clearly much lower than that of nitrogen in air. You do not need a lot of electrons to do a tremendous amount of chemical work. You can then also look at this in terms of, okay, so given different electric fields, where does the energy go into? And what you will see is that at low electric fields, you mostly start vibrating around these molecules. Why is that? That's because the energy required to start vibrating molecules is relatively low. If you then go to slightly higher electric fields, you start dissociating and electronically exciting molecules. And then finally, a little bit above 100 Townsend, you also start creating ionized molecules. And these ionization processes, they are not really relevant for combustion, but they are required for the plasma. Right? If you are not able to ionize any molecule, they do not create extra electrons, and well, there is no plasma. So what do we have so far? Assume we have a known reduced electric field, which is a nice pill shape which goes a little bit around above 250 Townsend. What we have is that for this reduced electric field, within 15 nanoseconds, we go from effectively 0 electrons in our gas to 1e minus 4 electrons. So that's like a 10 order of magnitude increase in a time frame of just 15 nanoseconds. That's a huge amount in a very short time. So this is the main challenge of plasma-assisted combustion, is that you have time scales which are way shorter than you already are used to in combustion. If you would view it as like, okay, where will ignition start? Well, ignition in a normal mixture will take in the order of milliseconds. That's ages compared to nanoseconds. And in a similar fashion, you also very quickly start populating vibrational states. You can also dissociate molecules and create electronically excited state. So for example, electronically excited oxygen or electronically excited nitrogen. In general, this plasma is able to, within the time frame of several nanoseconds, produce species at a hyperfast rate. Okay, so just to recap this first part of the lecture, our plasma is created by accelerating electrons in an electric field, which then can ionize and dissociate and do chemical work. These electrons can have a very high energy at a low temperature, which means that they can do chemical work. Reaction rates with electrons generally depend on the strength of the electric field. And the last part is the important part for the plasma-assisted combustion application. Electrons can be used to dissociate molecules, which means that they have the potential to replace initiation steps in ignition, for example. And at this stage, you might be wondering, what are these vibrational and electronic species? At least it was one of the things that I think I can safely say I struggled a bit with my first year. You have all these crazy names for everything. What's this? Why should we even care? So consider a molecule, and it has an electronic configuration. So in the classical Bohr model, you have these shells with electrons in it, and they can be moved up by a single shell. When you do quantum mechanics, it's a little bit more complicated. But the important consideration here is that if you have a molecule and there are electrons in their shells, depending on the way that those electrons are configured, the interaction strength between the individual atoms is different. And this then creates a potential which allows these atoms to be vibrating around inside of this potential. And because of quantum mechanics, this is quantized, and you have specific levels at which you can have vibrational energy. And even when you have this molecule, it can also rotate around. And what we classically assume in combustion is that all of this is in equilibrium. Which means that these electronically excited states or vibrationally excited states are species that we have always included in our models. But they are hidden away in our thermodynamic data. Right, so you have these NASA polynomials. I think most of you will be very familiar with them. And they are a way to show the temperature dependence of heat capacity as a function of temperature. And all these electronic configurations, vibrations, and rotations, they are tucked away in that thermodynamic data. Which means that now suddenly we have something to consider. If we want to have a plasma-assisted combustion mechanism to be consistent, we will need to be a little bit careful with the way that we do the thermodynamic modeling. This is something that I looked at somewhere during my PhD, and what I found was that when you have literature models and you do chemical equilibrium calculation on it, is that it can happen that you have a reduction in the adiabatic flame temperature because the thermodynamic data is not modeled consistently. I looked at it and made a consistent method to do this, and in that way we are able to exactly recover the original adiabatic flame temperature. And why is this important? Well, if you want to, for example, predict nitrogen oxide emissions, and you look at the rate limiting step, then you will see that with this reduced adiabatic flame temperature, you will significantly underpredict the rate constants of this reaction by around 70%. And as this is in the thermodynamic data, this inconsistency, it will be present at the entire burn site. It's not a matter of it will diffuse away or something. It's inside the thermodynamic data. It's in the coupling between temperature and energy. I'm already going to give a hint away, and that's that these inconsistencies arrive because we should be consistently counting the internal states of molecules. Okay, so where does this thermodynamic data come from? Well, the enthalpy is just a measure of the probability of finding a given internal state and the energy of that internal state. And we can find these probabilities by assuming a Boltzmann distribution. And if we then take a temperature derivative of this, we can get the heat capacity. And then what you will see is that at this low temperature, at around 300 Kelvin, the oxygen molecules and the nitrogen molecules will only be rotating around and translating around. That's because the average collision doesn't have enough energy to start vibrating these molecules. If we then start to increase temperature of our gas to 1500 Kelvin, then the average collision has enough energy to start vibrating molecules, which means that we store energy in the vibrational mode of nitrogen and oxygen molecules. In this case, the spheres are data from a database, and the lines are computed with my model. If we now want to model a plasma consistently with the thermodynamic data, and we would look at the electronically excited state of a molecule, then we want to separate out this electronically excited state into its own species. What does that mean? That means that the thermodynamic data of this species should only consider this electronically excited state with all of its internal vibrational states and all of its internal rotational states. And we should assume that all of this is in equilibrium. And then also redefine our original ground state species to exclude this electronically excited state. Right? So the probability of then finding a given internal state, a given energy, is then given by the Boltzmann distribution divided by the partition sum. If we do this, for example, oxygen in a singlet state for which thermodynamic data is available, then we are able to exactly recover the data that is available for it. And we can also do the same thing for the enthalpy. What is often done in literature is that when we want to model this oxygen in the singlet state, is that we assume that the energy of this excited oxygen species can be obtained by having the original polynomial and then adding an offset enthalpy to it. And in the case of this oxygen species, this still works with a reasonable accuracy. What means is that this will not significantly impact the adiabatic flame temperature. But if we then proceed and we want to develop even more detailed models where we also want to include the vibrational levels of molecules as individual species, right? So for example, we have the ground state of oxygen and the vibrational states within the ground state of oxygen. We want to separate, to model as individual species. Why do we want to do this? We will want to do this because we can then capture the non-equilibrium effects within this. But again, we take the sum of only a single vibrational level, and we make sure that we remove it from the other data. What you will then see is that the heat capacity of oxygen in the vibrational first excited state is no longer a function of temperature, but it's completely constant. Why? Because this oxygen molecule cannot vibrate around. It's stuck within a single vibrational frequency, but it can still move around and rotate around. This means that if we plot the data for the vibrational state and also the data of our previous two examples, is that we get this red line, which is no longer parallel to the other lines, but it is slightly skewed. Which means that if we would obtain the thermodynamic data of this species by this offset method, we get significant differences in the enthalpy at higher temperatures. Okay, let's go into a practical example. So we have a model, a chemical model where we want to resolve the vibrational states. So we have the ground state, we have the first vibration excited state, second vibration excited state, and we include all of these into a chemical mechanism as individual species. If we would now do a sweep of equilibrium calculations. So that means that you have the thermodynamic data of all these species are parallel lines going slowly up. If we would now do a sweep in temperature and run equilibrium calculations on this mechanism, is what you will see at low temperatures. We only have oxygen in vibrational ground state. And then when we start to increase the temperature, we start to populate first the first vibrational excited state and then the second vibrational state. And if I would have to run more, you would slowly start to populate more and more of these internal states. Which also means that as we heat this mixture, while it's remaining within equilibrium, we basically have a mixture which is continuously reacting, right? There's a given amount of chemical heat release associated with this process. Excited states start requiring more and more energy, while we release a little bit of energy from the ground states. And if you now would do that for all species, of all the individual vibrational levels, and you would take the sum of it, then you see that you get a effective heat capacity addition, which is going slightly up. If we would model this mechanism where all these individual vibrational levels separate, and would look at our original oxygen species, then we are able to exactly recover the thermodynamic data of the species. Which means that the heat capacity, which was originally inside of the thermodynamic data, is now inside of the chemistry, which is rather different from what it normally is. But it also means that we can now have different distributions than we would normally assume, where you have the equilibrium distribution. If we would do exactly the same procedure with the inconsistent thermodynamic data, then we see that the oxygen heat capacity is significantly over-predicted at higher temperatures. If we then go back to our adiabatic flame temperatures, then this is exactly the reason why the two models from literature underpredict the adiabatic flame temperature, because we are counting twice, in this case of nitrogen, the vibrational energy. Okay, so how far have we gotten until now? We had a plasma, right? And that's there because of electrons, which are accelerated by the electric field. These electrons, they have a very high energy and low temperature. The reactions with electrons depend on the strength of the electric field. They can dissociate molecules. And when we start including excited state species into a chemical mechanism, we have to be a little bit careful with the way that we do the thermodynamic modeling. But now the big question is, why is plasma-assisted combustion such an interesting topic? What's the role of the excited state species? And why should we even care? What is plasma-assisted combustion? I guess this is going to be the answer of our final part. Right, so very quick recap, the vibrational levels that we have. If we would have an air model where we have individual vibrational levels, is that we can have a plasma at the beginning. We create highly excited states of vibrational levels. And then that's our plasma in the beginning. And then you have a process called vibrational relaxation. That means that in the case of nitrogen, you have for example, VS2 state colliding with VS0 state, and then one will go a level up and the other one will go a level down. This creates an equilibrium between the vibrational levels, but not an equilibrium with the gas temperature. Typically, this is a process which is faster than the other process, and that is vibrational translational relaxation. And then this is the process where you only have one of the two changing a vibrational level. And that does create an equilibrium with the gas temperature. Right, so we went from a unpopulated vibrational levels to creating a lot of excited states, to having VV relaxation and creating a vibrational equilibrium. And then finally, at a time scale a little bit more than a couple of milliseconds, we have vibrational translational relaxation, and you get an equilibrium with the gas temperature. This is why we had to include these species in our chemical model, because we want to capture these effects. One of the reasons why we want to capture these effects is because these vibrationally excited states, they also apply a reduction in the activation energy of reactions. And so you can, for example, imagine if you are slightly lower inside of this potential, then the difference between the vibrational energy level and the dissociation of the molecule is reduced basically by the energy of this vibrational level. Which, in the case of Thales mechanism for nitrogen oxide, means that, well, the reaction rate becomes significantly shorter when you start populating vibrational levels. Generally, in plasma-assisted combustion, starting to populate nitrogen vibrational levels is something that you do not want. Why? Because you're storing energy in vibrational levels. This energy is not available in terms of kinetic gas energy, so it doesn't provide a temperature increase in the gas. What it will provide is an acceleration in cell-Diffusion mechanism, and thus produce extra nitrogen oxide. The different kind of excitation was the electronic excitation. In the case of oxygen, you have two electronically excited states, which are relatively low in energy, which are the A1 state or the A singlet state and the B singlet state. Again, in our plasma, it's produced at a very short time scale. And then and then it can remain for a relatively long duration stable during in a plasma. Because also these electronically excited states are at a slightly higher energy level than the ground state, they generally also provide a reduction in the activation energy of reactions, which can then provide an acceleration in reactions with, for example, methane. And this is something beneficial. So we would like to see these kinds of electronically excited states being produced. A large part of our gas in air is, of course, existing out of nitrogen. These nitrogen electronically excited states, they are at a significantly higher energy level than in the case of oxygen. In the case of oxygen, they are at around 1 electron volt, the lowest. But in the case of nitrogen, they are above 6 electron volts. They are that high that they are even above the dissociation energy of oxygen molecules. And one mechanism that they play a role in is that in a fast gas heating mechanism. There's a lot of potential energy stored in these nitrogen vibrational states, and they are relatively short-lived. Which means that within a time scale of several nanoseconds, they are produced in our plasma, they start quenching with each other, and they provide a very fast mechanism of gas heating, which means that the gas temperature can rise within around 5 nanoseconds by, in this case, 50 Kelvin, but can even be significantly higher. That means that this gas now is hotter, still relatively cold, but if you would have a higher energy discharge, it would be at much higher energy. And then you have higher temperatures, which accelerate reactions. But in the case of nitrogen electronically excited states, they can also quench against oxygen. And in that case, the potential energy within this electronically excited state is higher than the dissociation energy of an oxygen molecule, which means that it has the ability to dissociate this oxygen molecule into 2 oxygen atoms. And this is much more beneficial because that replaces slow chain initiation reactions by very fast quenching reactions of nitrogen electronically excited states. And then they can produce the initial radicals that we need in combustion processes. This can be oxygen, but it can also quench against methane. And then you can produce CH3, CH2, or hydrogen atoms. The case of electronically excited methane is a little bit different, and that's because it's very often assumed that electronically excited states of methane are dissociative, which means that the cross-section data that we use in our calculations to obtain reaction rates is often assumed that these electronically excited states, when they are produced, they will immediately dissociate into fragments. You can also, of course, have other bad gases. So if you would do experiments with argon or helium, then you no longer have rotation or vibrational excitation, which means that less energy is lost on these relatively useless processes. You get a higher degree of electronically excited states, which means that you overall get a much more efficient process of dissociating our fuel with quenching of electronically excited states or dissociating oxygen. Finally, a little bit of a example. That's considered a case for which experiments have been done in the literature. And this is a flow reactor where you have, at the beginning of the reactor, you have 2 electrodes which create a plasma. And then there is a long distance behind it where this mixture can react. This setup is placed in a furnace and it's kept at a constant temperature. Moreover, the conditions are diluted, which means that heat release is relatively low. The plasma energy is also relatively low. So it's basically a fixed temperature reactor where they are able to modify the temperature of the reactor by a setting. And then the measurements that in this case have been done is at the exhaust, they have put a gas analyzer and they measure the composition of gas. I have made a model for this, where I model this as a plug flow reactor in a 0-dimensional framework. I model the reduced electric field, and then depending on the temperature of the reactor, the mixture either receives 40 discharges or 140 discharges. The chemistry that I use for this is a 250 species chemistry with 1800 reactions. Timescales will be going down to picoseconds all the way up to seconds for the end of the reactor. And the modeling of the thermodynamics is, of course, done with my consistent thermodynamics model. The model for the reduced electric field is based on an equivalent circuit model. I will not go into detail of this, but basically it's a dielectric barrier discharge setup, and dielectric materials do not allow electrons to move through it. From an electrical engineering point of view, you can model these dielectric materials as a capacitance, which means that you can store charge on them, but they will not let charge through. This is done to avoid a very hot plasma, and this is the model that I use for that. My chemistry is based on a lot of different papers. I took the base of the mechanism from Benedicta group in a very recent paper, and then I re-added some stuff back in. Okay, so how does this look like this typically? So we have a very diluted mixture where we only have 2000 parts per million of hydrogen, 3000 parts per million of oxygen, and the rest is argon. Experiments are done in this reactor at 405 Kelvin, which means that there will be 140 plasma discharges. At a short time scale, we start producing these electronically excited argon, and they very quickly quench. It's very similar to what you would see, for example, in nitrogen electronically excited states. So they quench aggressively against oxygen and hydrogen, which then is the process that dissociates these molecules. If we then zoom out a bunch and our plasma is having a pulse frequency of 1000 kilowatts or 1000 hertz, then we see that we have very specific or very short times in which we produce a lot of radicals, which then slowly react in our combustion mechanism with the fuel or recombine back. If we then zoom out a whole bunch more, then we see that we have this beginning part where we have the 140 discharges and then the reaction zone after it. And you see that at this very low temperature, we oxidize around 5% of our fuel. If we then increase the reactor temperature and we reduce the number of discharges, then we see that we start oxidizing more of the fuel. Why is that? Because we have these radicals that are produced in our plasma, and after these radicals are formed, we need conventional combustion chemistry to take over. And at a higher temperature, this conventional combustion chemistry is just a little bit faster. If we go even higher settings, we start dissociating even more, or we start consuming even more hydrogen. And if we go to one of the higher settings, then we completely oxidize our fuel. We can record at the outlet of these simulations what the composition is, and then compare them to the experiments done by Solas in America, and then we can see that we can obtain a very reasonable match in these experiments for hydrogen. Similar thing has also been done for methane, and again you see that we can get a very nice agreement. We can also look at the heat release. So we have this plasma at different temperatures with different discharges. What's the fraction of heat release that we are able to extract at these lower temperatures? And now we see a significant difference between hydrogen and methane. In the case of hydrogen, we have low temperature. And when we start to increase the temperature and have a plasma, we start to slowly increase the heat release of hydrogen. This is beneficial because that means that, well, we will soon be able to transition towards ignition and our plasma can be used more efficiently. In the case of methane, you see that we produce less than 10% of the heat released in these settings, and we have to go all the way up to the auto-ignition temperature before we suddenly get a spike in the heat release and we go to complete heat release. This means that our plasma is able to dissociate molecules, right? It is a very efficient thing to dissociate molecules. But after that, we have to form CO and CO2, and it's recombining stuff into larger molecules. And this is something that plasma-assisted combustion cannot help us. So our plasma can replace the chain initiation reactants, but cannot do anything after that. We can also look at mixtures of methane and hydrogen. And in that case, what we see is that on the left, we have a completely methane mixture, and on the right, we have a completely hydrogen mixture. Is that at low temperatures, the addition of methane in a hydrogen mixture, so going from the right to the left, very quickly suppresses the low temperature heat release that you see in hydrogen. To conclude this webinar, so the plasma allows for the creation of high energy electrons at low temperature. These high energy electrons allow for the creation of radicals at temperatures that you would normally not see in conventional combustion. These reactions can then replace slow initiation reactions, and in the case that you're interested in ignition, can significantly reduce ignition delay. But something that you do have to consider is that you have a fuel-specific low-temperature chemistry, and depending on the fuel of your choice, plasma-assisted combustion might be more efficient or less efficient. But accelerating the inherent low-temperature chemistry of a fuel is apparently a tough question. I would like to thank, first of all, my supervisors over the past 4 years, Jan van Dijk and Jeroen van Ooyen, for helping me and supporting me doing my research. I would also like, of course, to thank the Dutch section of the Combustion Institute for giving me this opportunity, and all my colleagues who over the past years have heard me ramble on about plasma combustion. I hope that I could have given some insight in the intricacies and the interesting stuff behind the scenes.
Thank you very much. It was